Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be answering question 2.8 of section 1. So let's begin. This question asks us to basically prove the projective version of proposition 1.13. So it is useful to give proposition 1.13. So proposition 1.13 states affine variety y in a to the n has dimension n minus 1 if and only if y is equal to the affine vanishing set. Oh goodness. Y is equal to the affine vanishing set of some polynomial. The affine vanishing set of some polynomial where f is a non-constant irreducible polynomial in a from x1 through to xn. Now a quick corollary of this. Let us have some prime ideal in some polynomial ring. Let's say xr. Then the Krull dimension of the quotient ring is of dimension r minus 1 if and only if P is the principal ideal generated by F, where F is a non-constant irreducible polynomial in k from x1 through to xr. This essentially just uses this above proposition with the Nullstellen sets' bijective correspondence. Now we apply what we have here. So the dimension of y, let me change y here to something else. W. The dimension of y equaling n minus 1 imply, well, if and only if, the dimension of its homogeneous coordinate ring is equal to n by question 2.6. Now, s of y is equal to, or is defined to be, xn over the ideal generated by homogeneous elements vanishing on y, which is isomorphic to x0, well, x1 through to xn plus 1 over over I of y tilde, where the tilde is just the image under this bijection, or this reassignment. Now, I of y is prime because y is a variety, projective variety. So let's call this star. Where f is a non-constant, irreducible polynomial in k from x0 through to xn. Now, the non-constant gives you positive degree, irreducible is irreducible. The only thing that we have left to show is that f must be homogeneous. Or rather, because I of y is a homogeneous ideal, it must be d equals 1 to n. I believe it's 1 to n. I will just check this live. D equals 0 to n. No. Now, let's see. If f is not homogeneous, then I of y is of the form r times f, where r is within the homogeneous coordinate ring of p to the n. Now, f is equal to let k be the minimum such that fk is non-zero. Now, let r be within k from x0 through to xn. If r is not a form, if r is not within S of I for any I, then r is equal to r0 dot 2 let's just say d. and then E. Let J be the minimum such that J is non-zero. Suppose Suppose D is not equal to K, and suppose E is not equal to J. Then R times F has multiple forms, namely R times E F times D is the maximum, plus dot dot dot, plus Fk multiplied by Rj. Thus, for R not a form, and a form is just a homogeneous element. For R not a form, R multiplied by F is not a form. Not only that, but if R were a form, then Rf is not a form. The only exception is 0. Thus, if F were not homogeneous, then for all D, but I of y is not equal to 0 because 0 is the ideal generated by p to the n, and the dimension of p to the n is not equal to n minus 1. It is equal to n. Oh, and what did I write over here? Because infinity, not n. I of y intersect SD, Si, I guess, because I indexed by I. But the intersection of I of y with 0 is just 0. And the direct product of the 0 ideal is just going to be 0. Now I of y is not 0 because blah blah blah. Hence, f is homogeneous. And we are done. Y is the vanishing set of f for f homogeneous polynomial of non and it's of positive degree because it's non-constant. Which is what we wanted to show. Thus, we are finished. Thank you for watching. Goodbye.